If you're like me, you probably got curious once about what actually happens when we run our programs. How is a program written in a high-level language realized on the hardware? There's this great book that talks about exactly that. It's called The Elements of Computing Systems. In this video, I'll try to distill the main ideas from the book and talk about the stages a program goes through when we run it. Let's say we write a program that calculates the factorial of a number using a high-level language. The book uses a simple Java-like language called Jack. So let's go with that. This is what the program looks like in Jack. Now, the hardware, that is, the CPU, can only run a set of instructions based on ones and zeros as defined by the processor designers, say Intel or AMD. This low-level representation is called machine language. We'll get into more detail on the instruction set and what it means in later videos. For now, let's just say that the program needs to be expressed in machine code, that is, ones and zeros, for the CPU to run it. How do we get from a high-level representation to machine code? This is done by the hard-working compiler. Programs are not compiled straight to machine code, however. They are compiled to a human-readable representation of machine code called assembly language. Assembly language acts as a bridge between high-level languages and machine code, allowing low-level programmers to debug, understand, and possibly optimize the generated low-level code before it's transformed into machine code. The process of transforming assembly code into machine code is called assembling the code. This is done by an assembler. Assembly code has a one-to-one relationship with machine code, where every assembly instruction is translated to a corresponding machine code instruction. But even the compilation from high-level language to assembly code is not done in a single step in some languages like C# and Java. It is done in two steps, in what is called 2T compilation. The high-level code is compiled to an intermediate representation called VM code or intermediate code. The VM code is then translated to assembly. Why is that, you may ask? One of the main motivations behind 2T compilation was platform independence. As computing platforms started to proliferate, programmers needed a way to run their compiled programs on multiple platforms without needing to recompile and maintain different binaries for the different platforms. With an intermediate representation that is platform agnostic, the compiled code could run on any platform with the compatible runtime environment. The intermediate representation is obtained via the first T of the compilation. The VM implementation then did just-in-time compilation to go from the intermediate code to machine code on the target platform. Platform independence also made it easier for new platforms to support the language with a 2T compilation process. This is because a new platform only needed to implement the VM machine or compatible runtime environment that can translate the platform-agnostic intermediate representation generated by the first tier of the compiler. The process of going from the intermediate representation to the needed machine code is much easier than going from the high-level language to machine code. This is because the intermediate code is lower level than the high-level language it was compiled from. Once the runtime is in place, the platform could run any code compiled for that language. In contrast, supporting a language with 1T compilation meant developing and maintaining platform-specific compilers that can generate machine code for the new platform. This was much more resource-intensive. Usually, the trade-off between 2T and 1T compilation is that of portability, ease of development, and safety, at the expense of some performance overhead and direct control over the hardware. Java and C# use 2T compilation, while C and C++ use 1T. So there you have it. We compile our high-level programs to an intermediate representation called VM code. The VM code is translated to assembly code. This makes up the 2T compilation process. Assembly code is assembled to machine code with which it has a one-to-one relationship. The CPU then runs the machine code. In future videos, I'll go into more detail about how each step is done. Until next time.